Now we come to a very special type of intermolecular interaction, which is called halogen bond. But first of all, what I want to mention about the halogen bond is the theory behind the halogen bonding is not very clear. We have seen some kind of this interaction with the component of halogen atom in the molecules. We can see some interaction, right, in some specific environment, in some very low energy states, like in solid crystal structure. We can see the interaction between halogen with other kind of atom in a specific way. But we are not really sure that what really happens here, whether it is the electrostatic interactions or it is a kind of orbital interactions between atoms or between molecules. So it's quite hard to explain, but anyway, we also have some explanation. We can describe something, we can explain something, but not truly 100%. Okay, first of all, I want to introduce the molecules halomethane over here. So as you can see, this is a very simple halogenated hydrocarbon compound, methane with one halogen atom. So talk about the methane, halomethane over here using kind of molecular orbital theory. The HOMO structure of this one is somehow like this. The electron clouds around your halogen is kind of because of the sigma bond or sigma orbitals. As you know, if we want to construct this, we have to use S and P of halogen to combine with the wave function of carbon atom. So at the end, we end up with sigma, sigma star, and things like that. Okay? So, or you can also make it simpler by doing sp3 of carbon and 3 hydrogen atom first. After that, using the molecular orbital of CH3 in kind of tetrahedral structure and then combine with the orbitals of the X. So at the end, you have this kind of thing. So by calculations, we know that the area here on top is slightly negative. Top and bottom is slightly negative. And the area at the opposite side with the methyl group is slightly positive. So the area which is slightly positive over here is called the sigma hole. Okay. Or actually it's a hole of electrons, right, in the sigma orbitals. Don't forget that we are talking here about the molecular orbital theory, right? So this is sigma hole because it's the whole electron holes in your sigma orbitals. So as you can see, we have positive, we have negative charge electrostatically. So at the end, we can have kind of intermolecular interactions around the halogen atoms in the molecules using positive and negative charge like this. So first of all, if we have this molecule, I just copy and paste. We have so many possible interactions, okay, around this area, because you have positive and you have negative. So if you like have the nucleophile or anything with very high high density of electrons, so by electrostatic, this negative electron pair can have interactions with the sigma hole here. And if the interaction is strong enough, then you can fulfill the sigma star orbital, right? And then cleave the bond here. Okay? This is the nucleophile, negative charge, interact with the positive. On the opposite hand, if you have electrophile, which is slightly positive. So you can have electrostatically interactions with the negative side of the halogen, which stay perpendicular with the sigma bond here. Right? So it's 90 degree, okay, comparing with the direction of nucleophile and direction of the electrophile. But more than that, if you have another halogen containing molecules, let's say if we have another halomethane, it can also interact with themselves by positive and negative charge as well. So this is the negative charge area. So you can have electrostatically again interaction with the halogen of the next halomethane molecule through the sigma hole. Okay. So this is the kind of general picture of halogen bond. So halogen bond can be halogen with halogen, okay, but it has to stay perpendicular to each other. This is interaction between molecular orbitals. So as you can see, it's a negative charge and the positive charge, right? They overlap with each other. So we can confirm that this is the orbital interaction if the van der Waals radii is greater than the internuclear distance. So that means we have some kind of orbital overlapping between two molecules, and then we can confirm that this is the orbital interactions, okay? And we can use the word bond. But anyway, as I said, the picture is not very clear. And not only halogen and halogen interaction, your halogen can also interact with something else, positive charge and the negative charge. Okay. So normally we can see this nucleophile interact with halogen. Right? This is quite common for halogen and the electron-rich species like nitrogen atom, oxygen atoms, and everything. Even in biological system in nature, we can also see this kind of halogen interaction as well. So this is the most common halogen interaction, halogen with the nucleophile. And we also have halogen and halogen as well, but it's quite rare and the interaction is not very strong. Normally we can see halogen-halogen interaction in solid phase, in some kind of crystal structure, because in solid phase, in the crystal structure, your molecules is in very low energy state. And the weak intermolecular interactions can trap it, stay still, and we can observe the intermolecular interaction we can observe the very weak intermolecular interaction in kind of crystal and solid phase. Okay. Now this is the basic principle of halogen bond. I will show you some example and we'll have to discuss about it. From the halogen bond, so we're quite sure that we have interactions of hydrogen and atom molecules by these kind of things. Right? We have sigma hole and we have negative charge. We have interactions with positive and negative molecules. So iodine, as everyone knows, we have iodine in crystal, right? Because it's solid and we can crystallize it into crystal structure. The iodine bond length in iodine crystal is about 2.715 angstrom. But iodine can also have co-crystallized with something else. Okay. Now, if I co-crystallize the iodine with this molecule, okay, what we can see from the crystal structure that they align together like this in a linear long chain, because the nitrogen over here can also interact with the iodine, next iodine as well. And we have kind of linear polymeric chain, right? 180 degree over here. Okay. And as you look at the iodine bond length is 2.733 angstrom. And if I change the molecular structure of aromatic over here a bit by put 4 substituent methyl group into the ring, As you know, methyl group is electron donating group, right? So put it into the ring, and what happened here is the iodine bond length is shifted again. So in the crystal structure, this is still in the polymeric chain, linear polymeric chain as well, 180 degree and everything, similar to that one, but the bond length is shifted. Okay? So if the bond length is shifted, that means we have molecular interactions, because the bond length shifted means bond weakening or strengthened by environment, by other neighbor molecules. Okay, so I want you to explain why bond lengths are shifted in this way, okay, using halogen bond. Okay, and I will give you the correct answer in the next video.